All right. So welcome everybody. I'm Raffaella Carloni from the University of Twente in the Netherlands, and I will be chairing this session on unmanned aerial systems and legged robots. And we are going to have 20 fast 3 minutes presentations, but before of that we have a keynote speaker here, which I'm very glad to present. So Professor Paul Ho from the University of Nevada, Las Vegas, he's just moved there 1 month ago, he mentioned. He is an expert of unmanned aerial systems, and he will give a talk titled Material Handling Paradigms for Humanoids and UAVs. So the floor is yours.
Thank you. Okay, Raffaella, thank you very much for that introduction, and thank you all for sharing your afternoon with me and giving me the opportunity to kick off this final session of what's been a very wonderful conference. Some of you might know or followed my research. A lot of it kind of stemmed, it was motivated because of 9/11, and shortly after that because of Katrina, where we were starting to think about how can we use robots for disaster response. And so some of the things that we ended up doing is that we were interested in flying indoors. We were also interested in flying in tunnels and caves. And so we were looking at a lot of the technology at that time, as well as working with optic flow sensors for collision avoidance. For caves and tunnels, we started looking at how could you transition from loitering into a hover mode with fixed-wing aircraft. So that was kind of the work that we were doing. And then something happened where I got involved with humanoids. And a lot of my colleagues were saying, well, what are you doing at humanoids now? You're doing things with UAVs. But if you remember around this time, the word globalization started to really catch on. I mean, today it's very common. But in 2006, this is when Thomas Friedman had written his book, The World is Flat. And one thing, after spending a summer at Boeing, they were really concerned that American students in engineering just did not have experience going abroad, and therefore were lacking the skills in global collaboration. And so I approached the NSF with the idea of using humanoids as kind of a surrogate case study where we can have American students go to Asia, learn from the very best in terms of electromechanical engineering, as well as take the very best of the United States in artificial intelligence and information technologies. So that lasted to about 2012, and I thought I'd be finished with humanoids. I was wrong, because something called the DARPA Robotics Challenge came online, and it started to pique my interest. And hopefully by the end of this talk, you'll also be convinced with me that we are entering a new phase in robotics where we're really having material handling as kind of the business case. Okay, so at least I started to share a lot with my colleagues that I said humanoids and UAVs are the same thing, and especially when you look at it from the dynamics and the mathematics. And people looked at me very curiously. It starts to become very similar when you start to interact with the environment. So the number one rule with legged robots is not to fall down. Similarly, the number one rule in aircraft is never fall out of the sky. So it's kind of a stability issue. But when you start interacting, this is what starts to destabilize things. So if you imagine these types of robots that might be flying and actually have limbs that could actually do kind of machining operations for, like, say, bridge repair, you can imagine that there's instability that's going to arise. So a very, very fun control problem, okay? And it's not too crazy, because we know that we have underwater robots as well as those in space that do have manipulators, and they are also, instead of flying, they might be swimming or orbiting. So there is literature there to say that this is not completely crazy. Okay? So we kind of dubbed this MMUAV, or mobile manipulating unmanned aerial vehicles. we start to go back, revisit the classic literature, for example, Neville and Hogan and in peg and hold insertion tasks. But this time we added a manipulator to the flying robot, and just to understand what's involved, what changes in terms of the impedance control. Okay. We started to visit also the dual arm control. We mounted that on our quad rotors, and I believe my student gave a talk yesterday, as well as the interactive sessions, about valve turning. And then finally, we were looking at hyper-redundant manipulators, kind of like an octopus or a monkey tail. This one is an example of using a Stewart platform where we're revisiting the classic problems in visual servo, eye in hand tracking, and what happens when the vehicle is destabilized. So we're having a lot of fun doing these type of kind of whole body motion tasks and adding control to that. Okay, so going back to the DARPA Robotics Challenge, around early 2012, DARPA came up with this idea, motivated because of Fukushima and the tsunami. So there were 8 events, and so I just created this kind of notional video to kind of describe what's going on. So here I imagine the year 2020. It might be a devastated area. There's maybe biocontamination. It might be radiated. And what we learned in Fukushima, there was no absence of these types of vehicles there, but because of the radiation, we just couldn't go to ground zero. So they want the robot to drive the vehicle. So that was event 1. So in event 2, you can imagine the area is probably devastated. There's probably going to be a lot of debris. So they expect the robot to be able to walk over rugged terrain. For event 3, you can imagine there's debris in front of the door. So like any first responder or firefighter, you want to be able to move it out of the way, open doors, and go through them. Okay, chances are the walls are breached. So like a first responder, use your crowbar or sledgehammer or sawzall and breach through the wall. Next thing, it's a human-centered environment. There's probably ladders and stairs. Next thing is you want to turn these valves or switches. And then you want to maybe, replace a pump or connect a fire hose. Okay? So the takeaway of this is that it is a single robot that's kind of general purpose that's doing these types of events. Okay? And, I said by the year 2020, I think this is going to be realized. Just a show of hands, how many people think we're going to make it by year 2020? Oh, skepticism, I love it. Okay. In my expert opinion, I believe we're less than a decade out in actually seeing these type of things happen. Okay? So this is why I'm telling people, yes, maybe you saw the webcasts, you say, wow, it was really slow and things like that. But if you really look under the hood, actually, what is going on, I say that this is going to fundamentally change our world. Okay. Now, the big thing is when I first heard about the DRC, I said, this is the most outrageous thing. Who would be crazy to do this? Okay. Sure enough, yeah, it's definitely a very noble task for robotics to look at this. But I went to sleep, I woke up the next day, and I said, I have to do this. Because I've been evangelizing in my classrooms about what the future is going to be like, and I said, I have to give my students the opportunity to say they are part of history. Okay? So I said, okay, I'm committed to doing it. But I said, how do I go against these Goliaths like Lockheed Martin and NASA? I mean, they have decades of experience and war chests of money. But then I said to myself, hey, I got 7 of these Hubos at Drexel. Okay? We have more Hubo humanoids than the Hubo lab in Korea. Okay? So, you know, with every Goliath, there has to be a David. Okay? So I said, I think we can be tactful, you know, about this. And so, you know, I created this band of brothers, and I essentially told them, I want you to make me an app. Okay? I want you to create a ladder climbing app, a driving a vehicle app. And as a result, I would distribute these robots to my band of brothers so they could quickly put something together. Okay? So this was about 3 months before the Miami finals. This was about 15 months of nonstop, you know, development, testing, evaluation, validation. And, you know, we could see that we got actually Hubo. He's in the Polaris ATV. We can steer, we can brake. So, you know, things were coming together. This was event 2. DARPA call it the rough terrain event. This was with Ohio State and Professor Yuan Zhang's group, where they just demonstrated crab walking as maybe a tactic to climb over larger heights. Mike Stillman's group out of Georgia Tech, they were applying a lot of their knowledge about navigation amongst moving obstacles, applying things to actually do the debris clearing event. Matt Zucker out of Swarthmore had a lot of experience with DARPA Little Dog. He was applying his CHOMP algorithms for the door opening event. This was with Chris Hauser's group out of Indiana University, as well as George Lee's group out of Purdue, where we showed we could do ladder climbing. This was with Dimitri Berenson's group out of WPI, where they were applying their variants of RRT algorithms for the whole body motion planning and teleoperation of valve turning. And then finally, Peter Allen's group out of Columbia, they were using a lot of their techniques with grasping and vision to work on the fire hose attachment task. Okay? So, you know, we did a lot of mock trials and exercises and timed events. We were quite hopeful that we would get maybe on the low end 11, maybe 19 points. So, you know, we felt, okay, you know, a lot of our labor is going to bear some fruit. But then we all know what happened. And we ended up only getting 3 points in the Miami trials. And while I tried to keep a very stiff upper lip for my team, this is how I was feeling on the inside, okay? And I had to ask myself, was this just bad luck? Or really, was my best just not good enough, okay? So, you know, after 18 months of a very intensive schedule, I decided to take a 1-month retreat. And I just kind of completely escaped from the world. I locked myself up in a hotel in a non-disclosed location, and I read and I read and I read. Okay. The question I was trying to ask myself and what I wanted to share to all my colleagues is, what did we learn from the DRC? Okay? And so what was the real significance of it? And after I started to look at the old footage and do a lot of reading, I also a picture started coming to mind. So these are some other things, like the DARPA ARM project with manipulation, or Robonaut flipping switches, as well as we know that Google has been acquiring companies. This is another company that does recycle sorting. I was also studying what was going on in Europe, things like Codesys, as well as Arcus, as well as RoboHow, that it became very clear to me that we are entering this material handling situation, okay? And one could imagine that Shaft is a general purpose material handling robot. It is conceivable that it could do that, where it is really moving, exploring, and operating in the world like people or even animals do. Okay? So this started to raise another question because I was looking at the footage out of Fukushima and the cleanup that's involved. So we got to understand there's a difference between just response, which is the first 72 hours, but perhaps maybe less urgent, but equally important is the cleanup. Okay? So you can imagine in the cleanup tasks, there's a lot of preparing. For example, you have to cut up all these trees, you got to dispose of the debris, you have to do the recycling, you got to do a lot of the sorting and stacking. If you look at Katrina, the hurricane itself, it's still going on, and it has already cost over $4 billion. Okay? But what if we can actually have something like a material handling hubo, which could augment the worker to accelerate the task? Even if they can do a marginal fraction, we could save money as well as rebuild the society a little bit faster. But I think the evidence is showing that material handling robots for these type of general purpose tasks is within reach. Okay? So, I just want to talk a little bit about Vegas. A lot of people associate me with Drexel. I was there for 14 years. People ask me why I'm going there. I've been there for about a month. Some of you might know that Nevada was the first state to legalize driverless cars. I think Google's driverless cars has a Nevada plate. Okay. Also, earlier this year, the FAA has designated Nevada as one of the 6 states for UAV flight testing. Okay. And also, while many people know Nevada for its gaming industry, it also has a very rich aerospace heritage. Okay? So this combination where I can fly, there's a lot of material handling opportunities. It was just something that I couldn't dismiss, lightly, and so I decided to uproot and actually take a chance. Okay. Okay, so I'm just wrapping up. I just want to thank all the sponsors that have, made this journey over the last 14 years very enlightening. Okay. I like to also dedicate this to all my students because it was their blood, sweat, and tears that went into these slides. Okay? And of course, I'd like to thank all my teammates, my band of brothers that were on the DRC. And I'd like to especially dedicate this to my friend and colleague, Professor Mike Stillman. With that, I thank you very much for your attention. I hope you enjoy the rest of your conference.
All right. A very good evenings to you guys. I'm Hairi from Vehicle System Engineering, University Technology Malaysia, located in Malaysia. Fly away around 24 hours just for a 3-minute speech. So my paper is on a robust attitude controller for uncertain hexarotor MAVs. So the idea on this paper is to develop a robust controller whereby we consider uncertain disturbance on external disturbance, nonlinear dynamics, coupling, and uncertainty of parametics. So this is very simple controller whereby we cascade a PI and a PID controller, whereby this PI, PID to achieve desired output trackings, and we put some robust compensator to reduce the effects of the uncertainty. So the idea behind this is to implement on an onboard embedded microcontroller, which is we use a 16-bit microcontroller for a low cost, a small scale prior my timings. All right, so this is the hexa rotor that we use. This consists of 6 rotor in X configurations. We can consider a coupling and effects of the nonlinear dynamics and also the effects of external disturbance. This is very simple, robust altitude controller whereby we cascade inner and outer loops of P and PID to achieve ratings. And we use a robust compensator whereby this is more likely on a second order filters, where the idea for robust compensator is to retain the influence of the uncertainty, especially on the disturbance. So this is the simulations results that we have done. If you can see on the left is the nominal control, whereby this is just a PID controller. If you can see that the effects of disturbance is drifting the roll and the pitch of the controllers or the systems, and the robust controller on the right, whereby we have cancel out the disturbance. So this is the experimental experimental results, whereby on the robust controller on your right, you can see that we have restrained or reduced the effect of disturbance within the margin where we decide is between 2 degrees plus minus. And this will be the experimental result, whereby we experiment, we demonstrate in the open air. It's very strong wind at that time, so that's my student hands. So thank you, and I will, if you have any questions, I will be in the interactive session. Thank you.
Good afternoon to everyone. My name is Vincenzo Lipiello. I'm an assistant professor at the University of Naples, Federico II. My talk is about a backstepping approach for the emergency landing of a quadrotor in case of a propeller failure. My colleagues Fabio Ruggiero and Diana Serra are co-authors of this work. So everyone that works with quadrotor or multirotor know very well that the failure of a motor is a quite common, even if not frequent event. So what we propose in this paper is an active fault-tolerant controller that stabilizes the Cartesian position of a quadrotor in case of a complete fault of a motor, so allowing emergency landing maneuvers. So the proposed approach couples with the case of a complete fault of 2 opposite motors. So at the end, we consider a system, we achieve a system that has only 2 active motors, so we can classify this as a birotor. In this configuration, due to the presence of a permanent torque around its vertical axis, the birotor will continue to spin around itself. So we have several effects due to this. We lose, obviously, the capability to control the yaw, and we have, moreover, on one hand, a stabilization effect of the angle around the uncontrollable axis due to the gyroscopic effect. But on the other hand, the dynamic model of the system becomes similar to a mechanical system subject to non-anomic and time-varying constraints. So in this case, we propose a new control law, and we prove the stability of this control law that is able to stabilize the Cartesian position of this system in any point of the space. So this is the main control scheme that we propose. Is composed mainly in 2 parts: a low-level inner loop for the control of the pitch or the roll angle, depending on which motor is broken, and an outer loop that is composed of 2 parts. One is devoted to the control of the altitude, and another one is devoted to the control of the X and Y component of the Cartesian space. So we test this algorithm in simulation with different initial conditions and for different emergency landing paths. The results that we achieve demonstrate the effectiveness of the proposed approach. So thank you so much for your kind attention, and if you are interested to this paper, please reach me at the beginning of the interaction section because I must go. Thank you so much.
Hello, I'm Michael Dilley. I'm now at NASA Ames, though I completed this work while still a graduate student at Carnegie Mellon with my collaborator Ben Gukolsky and thesis advisor Sanjeev Singh. Suppose we are in pursuit of a fleeing evader that we know is constrained to lie within this road network, say this little area over here. Even within this small area, and just for the purpose of example, supposing that we had these convenient additional roadblocks that constrain the target to lie within this even smaller, basically trivial subgraph, we still face some fundamental challenges. For instance, given the presence of a cycle, we may find ourselves basically running in circles chasing the target. And the presence of branches, such as that at the lower right there, gives the target an opportunity to hide, such that when we pass by, it might sneak into the larger graph. And therefore, our approach is to apply something known as graph search. This is in a pursuit evasion sense, not a classical path planning sense, to the underlying road graph. And then, critically, map this abstract search to executable UAV actions. Our basic strategy then is to adapt an existing algorithm that essentially selects an approximately minimal set of nodes in the graph at which to place guards, so that we can then essentially unroll the graph into a tree, to which we then apply a well-known graph clearing algorithm that is essentially depth-first traversal. And this provides us a guaranteed capture strategy, providing of an absolute adversary in a game theoretic sense. And we build on this to develop a search strategy for unknown targets that we simply model as having potentially infinite speed, as well as a capture or recapture strategy of targets with known speed bound. Now, of course, what's most interesting about this is how we might apply this to UAV teams. The first step, of course, is to develop a set of action primitives mapping to the abstract search. And this mostly boils down to very judiciously reasoning about the location and motion of the sensor footprint. However, even more interesting is to reason about what's different about air vehicles from ground vehicles. For instance, they are not themselves constrained to the graph. And so instead of having to, say, backtrack to move between searching one part of the graph and the other, they are free to fly over open space if it is advantageous to do so, while at the same time, however, potentially being subject to somewhat complex kinodynamic motion constraints. And just to conclude, I'll present a simple example video here of an environment in which a target sighting was reported at the top. Our UAV team sort of started in the middle. 2 agents were dispatched to basically stem escape routes, and the rest of the agents were sent in to essentially mop up the interior. If you're interested in hearing more details or seeing a real-world example, please find me at the interactive session. Thank you.
Yeah, good afternoon. So my name is Jianwei Zhang. I'm from University of Hamburg, and the first author is Wei Kong, my PhD student. Unfortunately, his visa to US has been rejected, couldn't come, and I present for him. And this is a joint work with China, so the National University of Defense Technology, and there are a lot of authors since this is a system really implemented with a real or fixed wing UAV. I show you the video, and it's quite a complicated integration project. The motivation is autonomous landing with a fixed wing UAV using on-ground visual system. So here we show the system architecture. We use a stereo vision system with PTU, and this consists of 3 vision units along the runway. So you'll see here the setup. And here we show the more detailed contents. This is the data transmission and autopilot on board. And here's the left PTU and the camera system, and the right side, and these 2 systems are connected. So in this paper, we present also the theoretic model and the pixel deviation compensation model. So for this left and the right optical point, and here show the whole camera model. So we use the state-of-art tracking algorithm by other boost method. So here some of the real world scenario. So this system has been tested in Changsha. It's in the real field landing area with a 200-meter runway, and the technical specification of the pannier so listed precisely in the paper. So we show some of the result of the real landing, and let me show a short movie, and I'm sure if it can be. Sorry, why it's not coming? Okay, time running up. I'll show you in the interactive session 2 minutes landing movie. Thank you very much.
Good afternoon. My name is David Anthony, and I'm here to present my work on crop height estimation with UAVs. This was done in conjunction with my collaborators, Sebastian Elbaum, Aaron Lawrence, and Carrick Detweiler at the University of Nebraska-Lincoln. So why are we interested in crop height surveying? Well, crop height, and in this case corn height, is an accurate predictor of the overall health of a plant. It's a predictor of any stresses the plant may be undergoing, such as water deficiency, nitrogen deficiency, and so on. And early on in the plant's lifetime, the crop height can actually be an accurate predictor of the final yield of the plant. So this type of information is of enormous utility to both researchers and commercial producers. However, researchers very rarely use it, and commercial producers it's practically unheard of, mostly because we do it, as you can see in this picture, where some poor grad student has to go out into a cornfield and select a subset of plants and measure them by hand, which is not only time consuming, but eventually damages the field as you repeatedly traverse it. So in our work, we use small UAVs equipped with a laser scanner to automatically measure the height of the crop. This is very challenging as we have to deal with noisy scan data because we're operating in a very unstructured environment. As you fly over the cornfield, there's wind, so the corn plants move. You're also dealing with the corn structure changing as you encounter areas where maybe it was drowned out. And because we're using these small UAVs with short-range scanners, we have to operate very, very close to the crops, typically within under a meter to the top of the crop. So these two videos illustrate the scan data we collect as we fly over the field. The top video is kind of the view from the rear of the UAV, so you can imagine the laser projecting down, and this is kind of the noisy data you have to process on the fly. While the bottom video is the side profile of the same flight. And so you can see that even though a large number of the laser range readings are trapped in the top canopy, which are the kind of purple and blue hues, we still do get the occasional range reading that reaches the ground, which is the green and yellow hues. So from this laser scan data, we can fuse it with the IMU data and estimate both the top of the crop location and where the ground location is. So from this information, we can produce an online estimate of the crop height and the UAV posed above the fields. So if you come to the interactive session afterwards, we can talk about how we were able to demonstrate stable flight over these unstructured environments and produce with an automatic height controller with only the laser scanner and IMU data without using any GPS or anything like that. And we can form online estimates of the crop heights within 5 centimeters of hand-verified data. But we do this orders of magnitudes faster than existing state-of-the-art practices. And this enables a lot of interesting research opportunities, not only for robotics, but also biology researchers. So thank you. I'll see you afterwards.
I'm presenting on behalf of Danuka Abewernena, who couldn't be here today. We've all seen the amazing things that quadrotors have done indoors, like transporting wine glasses and traveling in beautiful formations. And what we'd like to do is take that same sort of amazing control and see it outside. So what happens when we take these vehicles outside? Well, we rely on low quality sensors, GPS, IMU, etc., and therefore have reduced performance in terms of our control. We also end up being affected by significantly larger disturbances, such as wind, that blow the vehicle around dramatically. And unfortunately, my video isn't playing there, so you don't get to see our Pelican dancing around with 10 meters of error as it's being blasted by moderate winds. So in order to address these two issues, what we'd like to do is take low-cost sensors, such as images, gyroscopes, and accelerometers, fuse them in such a way that we can simultaneously do good state estimation and predict or estimate what the wind is doing. So we can eliminate those effects before they happen, making the assumption essentially that wind disturbances vary slowly. So what we've done here is we've built a visual inertial fusion system based on EKF, and augmented it by adding a stronger and more capable dynamics model that incorporates the effect of wind on the vehicle. So the two main effects we see on these quadrotors are blade flapping and induced drag. And both of these effects essentially vary the vehicle position in the body XY position. And so we can incorporate their effects simply by a linear variation in the forces applied to the vehicle dependent on the airspeed as opposed to the body speed of the vehicle. So this adds only a small addition to our state, so we can add in wind states into our estimation process. And the question becomes, given that we have biases on our IMU sensors and given that we have these new wind states in there as well, is the system still observable? So we've completed an observability analysis, a locally weakly observable verification, and what we found is that we can detect the X and Y components of the wind, but only if we have accelerations in either the body X or the body Y direction. When we're stationary, or sorry, when we're at constant velocity, we lose the ability to detect the effect of wind. We have no ability to see the component in the Z directions. It's essentially the fact that we also have the thrust in that. So if we make some assumptions about what that our wind is being measured is varying smoothly, we can actually eliminate the Z direction wind component and return to a fully observable system and therefore do proper estimation. So we implemented this with a Parrot drone in a Vicon system, and we blasted it with a fan and ended up with about 1 meter per second static wind in the environment. And what you can see here is we get excellent position tracking, velocity tracking, and wind estimates on board the vehicle. Thank you very
much. Good afternoon. This paper presents an approach for inspection of pole-like structure using a vision control, vertical taking off and landing, unmanned air vehicle, and shared autonomy. My name is Inkyu, and Supervisor Peter Cook. This work is done in collaboration with Stefan Haber from Autonomous System Laboratories, SRO. Okay, motivation. An electricity company reported that there are 174 million streetlights in the United States, Europe, UK, and France. This number is equivalent to 2.4 times larger than iPhone has been sold by 2012, and 13 times longer than the Earth's circumference, assuming a streetlight pole is 3 meters. And we can imagine how many streetlight poles in there. And this streetlight pole need to require to be inspected regularly. How is it done today? This inspection task is done by licensed inspectors. They climb up a pole with rope, ladder, or cherry pickers, and then examine a pole by taking a picture. A skilled inspector can estimate important information about pole. However, inspecting vertical structures such as light and power distribution pole is a difficult task that is time-consuming and dangerous, expensive. In addition, the effectiveness of this method may vary depending on type of pole and the ability of an inspector. Recently, micro-VTOL platforms such as Cortexa and octocopters are rapidly gaining interest in research, military, even in public domain. The Unmanned, low-cost, and VTOL properties of this platform make them ideal for situations where inspection would be time-consuming and harder. Therefore, we try to develop an inspection system using these useful platforms. There are challenges involved in developing VTOL platform, a VTOL-based inspection system, such as flying in close proximity to a target where maintaining a fixed standoff distance from it, being immune to be wind gust, and exchanging useful information to the users. Okay, to overcome these challenges, we require accurate dynamic model of the air vehicle, high performance sensing, and good controllers to be implemented on the vehicle. Easy to control and intuitive interface are required to the human operator. So the contribution of this paper fall into 3 main areas. First, we develop a line feature-based, image-based visual solving for VTOL UAV close quarter maneuvering only using vision and inertial sensor. Secondly, we demonstrate the use of shared autonomy to permit an unskilled operator to easily and safely perform UAV-based pole inspection in outdoor environment with wind even at night. Lastly, the inspection system is evaluated with the ground truth in indoor and outdoor environment using motion capture devices and laser tracker respectively. Thank you for your attention, and it would be great if you could discuss more detail in my interactive session.
morning, everyone. My name is Rafik Mibarki. Our present project performed at Prisma Lab. So the project is about aerial robotics for assembly tasks. So the robotic system consists of UAV to which a manipulator is attached. And this robotic manipulator is actuating an assembly structure. And the objective is to automatically position this assembly structure into its target. For example, docking application. For example, the UAV base, we can have, for example, helicopter or quadrotor. Our initial contributions in this project has been first the design of a new visual controller scheme that endows the aerial robotic system with the capability of docking application using onboard vision. So we have a vision, we have an onboard camera attached to the UAV base, and this UAV base is watching a target, and the objective is to automatically dock. So the controller we propose allows to control the manipulator and the base simultaneously at the same time. The contribution I want to talk about in this presentation is about the cross-coupled dynamic effects. When the UAV moves, the dynamic of the manipulator will be affected. And on the other way around, when the manipulator moves, especially if it holds heavy weight, the UAV base might be destabilized. So it's very important to take into account this cross-coupled dynamics. So we proposed a low-level dynamic controller, taking into account these effects. The controller is based on an integral backstepping approach, and the key idea has been to control the UAV attitude dynamics as well as the manipulator dynamics at the same level. We have tested validated this method in simulations, considering large image noise, IMU noise, and 30% of modeling errors, 30% of the dynamic model. You can see the visual error converge to 0, and you can see on the bottom right the 3D motion of the assembly structure to reach the target. And on this video shows the corresponding simulation. So on the left, you have the aerial robotic system holding the assembly structure. This structure is characterized by 4 red points and the target by 4 blue points. And on the right, you have the variation of the features in onboard camera image. As you can see, this variation of the image is different from classical visual salvoing. And you can see on the right that we are able to reach the target, to dock the target, using only onboard vision. And here we have used only simple image coordinates, but in other works, we used image moments and we obtained better results. Thanks.
Good day. Good day. I'm Surya Singh, and I'm presenting on behalf of Paul Pounds and Jared Page. Paul sends his great apologies that he couldn't be able to make it today because of a family emergency, but he really wishes he could be here. We are here to present the Quadroller, a UAV UGV hybrid, yet another great example of ground and legs, or in this case wheels, coming together. So, fundamentally, aerial motion is generally energetically expensive, whereas rolling is cheap. Consider that, consider it this way, or put it another way. If you have to fight gravity, you don't have a leg to stand on. The trade-off, this trade-off presents an interesting surface for us to consider in terms of design. In general, we can actually take advantage of the fact that we can add the mass of a wheel and get the benefit of extended range and have the terrain mobility and terrain handling of aerial flight. Though, you've got to be careful when you're mixing two things, because as they sometimes say, two eagles sometimes don't make a wonderful aircraft. So let's see how this comes together. Well, since we're being very thorough here, I thought we would quote some Thoreau and just simplify. And in particular, we'll quote some Thoreau and simplify our quadrotor design. In particular, we're going to actually use the quadrotor design to make minimal modifications to the design of the quadrotor and just add a simple truck with 4 wheels. So basically what we've got is a total of 6 wheels, but only 4 will be on the ground. The tilted rotors provide propulsion to the ground, so really no modification of the avionics is necessary. This provides a much simpler design. If we look at the analysis of this, we see that we have effectively a skateboard-like structure, or somewhat similar to the snake board if you're familiar with that analysis. Here, lateral tilt induces a turning angle in the front wheels. How does this look? Well, it actually leads to some pretty easy and intuitive control. Driving and steering are fairly simple, and as you can see, we get much longer flight duration when we combine rolling and then instead of just flying alone. Similarly, we get decent performance on all types of terrain for both fast flying and slow flying, and for carpet, gravel, concrete, etc. So it's a very robust design. Thank you very much for your time. I hope you come by and see us at our poster, which happens to be during the last session.
Hello, my name is Jose Acevedo from University of Sevilla, and I'm going to present the paper Persistent Monitoring with a team of autonomous glider using static soaring that we have written in collaboration with the University of Sydney. Okay, the UAVs offers a higher, safer, and faster coverage from university for surveillance and monitoring mission than other type of robots. However, usually the UAVs have a very limited flight duration. On the other hand, the autonomous glider get to lengthen the flight by using the energy captured from wind currents or thermal. Therefore, we address a cooperative monitoring mission with multiple gliders from a frequency-based approach. The objective was to lengthen the mission using static soaring while minimizing the elapsed time between each pair of consecutive visits to any position into the covered area. Then it proposed a distributed solution, scalable, dynamic, and useful even under communication constraints, which allows the glider to patrol cooperatively the coverage path and access to the thermal in an orderly manner. Then there are two main problems here: to coordinate the glider to perform a path partitioning strategy from a distributed manner, and a location problem where the thermal had to be assigned among the glider to lengthen the mission. Further, distributed coordination to the path partitioning strategy is solved by using an algorithm based on the coordination variable. On the other hand, a method based on the one-to-one coordination is proposed to manage the access to the thermal. Once two gliders meet, they share information about the thermal, then they use this information to decide in an independent manner if it should change the segment with the other contacting glider, and as both gliders have the same information, both gliders have to decide the same action. Finally, a protocol to decide how long a glider has to remain in the thermal is introduced. The user approach assumes that based on the information about the coverage path and the glider model, it can estimate the required altitude to reach the next thermal. Therefore, if glider remains into the thermal, only the required time to gain this altitude. Some simulation have been proposed to validate the system. Here we can see how the glider changes their segments, the glider altitude, and the minimum elapsed time during the mission compared with other approach. And finally, it can be concluded that the patrolling strategy for long-endurance mission is possible using glider and static soaring. Thank you very much.
Hello all, my name is Vasilis Vasilopoulos, and I am here to present you a work done at the National Technical University of Athens with Iosif Paraskevas and my professor Evangelos Papadopoulos, which focuses on leg locomotion on compliant terrain using a viscoplastic approach. In this work, we focus on a monopod hopping robot with a single actuator. Past works on monopod robots like this from NTUA included a simple dynamics model with 2 degrees of freedom. The ground was considered completely stiff, and the foot acted as a revolve joint during the stance phase. In NTUA, a novel controller called Multipart was also developed for stiff terrain, controlling both the body's apex height and forward velocity with a single actuator. However, its performance was only tested on stiff terrain as shown in this graph. A viscoplastic contact model was developed in this work capable of describing fast dynamic running. This model is considered an extension to existing viscoelastic models, and it makes use of three lumped parameters, a stiffness coefficient, damping coefficient, as well as a coefficient of permanent terrain deformation to describe plastic impacts. This coefficient is implemented in a recursive form, so it allows the description of repetitive loading on a particular contact point. As shown in this picture, in a classic viscoelastic model, the contact ends with no permanent ground deformation. However, this is not the case in the viscoplastic for the viscoplastic model. This video shows a 5-kilogram ball falling from a small height with no initial speed. The ball hits on the ground, described by specific parameters according to the viscoplastic model, and bounces back. Due to the coefficient of permanent deformation, however, the contact curve does not return to 0 point as a permanent deformation occurs. For the incorporation of the foot-terrain interaction, an updated model of the monopod robot was used with 4 degrees of freedom, as the foot is no longer considered massless. The vertical force from the ground is introduced to the whole system through the foot. For the purpose of this work, we assume that a point contact occurs each time the foot hits the ground, and bulldozing effects are neglected. Finally, a novel controller for compliant terrains called XMP was developed for this work. It uses energy magnitudes, and therefore it does not require an estimate of the terrain properties. As can be seen from the video, it can quickly bring the robot to steady state and maintain the motion even with terrain alterations. The sensors it requires are limited to 2 encoders for measuring the robot leg length and leg ankle, as well as an inertial measurement unit for determining the main body position and the force sensor at the robot foot. Thank you very much. I look forward to discuss this matter with you in the following interactive session.
Hello, my name is Fumihiko Asano from JIRST, Japan. Today, I'd like to talk about our research entitled Passive Dynamic Walking of Compass-like biped robot with Dynamic Absorbers. In our previous works, we proved that rigid leg walkers can achieve high-speed passive dynamic walking, but the adaptability to rough terrain is not high, and that viscoelastic leg walkers can achieve high adaptability, but the walking speed becomes slower. And the purposes of this paper are fusing the both advantages of rigid leg walkers and viscoelastic leg walkers, and achieving high-speed and adaptive passive dynamic walking by using a simple mechanism, a passive dynamic absorber. Firstly, I'd like to show you some movies with rigid leg frames. The passive dynamic walker exchanges the stance leg instantaneously. However, in the case with viscoelastic leg frames, the passive dynamic walker generates non-instantaneous double rim support phase like this. And this is an experiment for overcoming a step. In the case of a rigid leg walker, it cannot overcome the step. However, a viscoelastic leg walker can overcome the same step in the same situation. So viscoelastic leg frames achieve high adaptability to rough terrain, but the walking speed becomes slower. So we have to conclude that there is a trade-off between the adaptability and the walking speed. So based on the observations, in this paper, we discussed the following problems of how to achieve high speed and adaptive passive dynamic walking, and how to improve the adaptability without decreasing the walking speed in passive dynamic walking. And in order to fuse the both advantages, we can consider this walking model with dynamic absorbers. So the dynamic absorbers attached parallel to the leg frames provide indirect softness in the leg frames for achieving efficient bipedal locomotion. And first, we developed the mathematical model following Lagrange method. And second, we performed numerical simulation and showed that passive dynamic walker with dynamic absorbers can achieve high-speed walking. And in the interactive session. I'd like to explain the detail. Thank you very much.
Good afternoon. I'm Brian Satzinger from UC Santa Barbara, and several of my collaborators and my robot are from JPL, so I'd like to acknowledge them. My focus is on walking autonomously with a quadrupedal robot on very rough terrain, and this robot is a competitor in the DARPA Robotics Challenge. So RoboSimian is a robot that has 7 degrees of freedom on each of its 4 limbs, which are all identical, compared to more typical 6-degree of freedom legs that you might see on a walking robot. This is because the limbs are used for manipulation and for locomotion, and while that freedom is desirable for manipulation dexterity, it becomes a liability for walking. Although we have access to good analytic and numerical inverse kinematics, or IK, solvers, there are in general infinitely many possible solutions, and naive approaches can eventually place the robot into pathological configurations that are very different from the nominal walking pose. So to back up, we could make RoboSimian act like a 3-degree of freedom limb robot like Little Dog by creating an inverse kinematics function to map the Cartesian end effector location to all the joints and just treat it like it's a 3-DOF robot all the time. But that would really waste a lot of the robot's capabilities, although it would avoid all these pathological situations if we chose the right function. So instead, if we've designed such a function, we can use it sometimes to clue us into what's a reasonable IK solution, and other times use the full capabilities of the robot. And our approach is designed to work well with random sampling planners, in particular RT Connect. So we plan the initial and final joint angles on all limbs for a given motion by looking it up using that IK table. And this gives us a known reasonable goal pose, which is really useful for using RT Connect. And in between that initial and final position, we allow the swing limb to follow an arbitrary full 7-degree of freedom path. And this allows the full use of the limb's capabilities to avoid obstacles while remaining stable, if you imagine there's debris around the robot. We can also use one of the stance limbs to define the body pose relative to that limb's foothold. And so this means that all the dimensions in the search space are actually physical angles and radians. And then the remaining 2 limbs, we just do another IK table lookup during the motion. So they're dependent on what the dominant limb is doing. So those don't contribute dimensions to the search space. So here's a video. There's a lot more to this that I'd be happy to discuss in the interactive session. The benefits of this approach are we avoid these pathological situations. We know the goal pose in advance, so we can use RT Connect. We can do offline analysis, and I'd like to emphasize that we get kinematic closure for free, so there's a non-zero probability of a random point in search space being feasible, which is really nice. And in conclusion, I would like to bribe everyone with this local delicacy to please come to the interactive session. Thank you.
Hello everybody, my name is Mazia Sharbafi. I'm working with Andre Seifert in the Locomotion Lab, and this work is done in cooperation with SIM Group in TU Darmstadt, and it is about helping control of the musculoskeletal biped robot called BiBiped. And our approach is dividing the locomotion into 3 sub-functions: bouncing, which means axial leg function of the stance leg, and swinging, which means the rotational leg function of the swing leg, and balancing, which is postural control of the upper body. We start from the BiBiped robot. We have a very detailed simulation model of the robot. We control that, and then we finally implement the control on the rear robot. But the result of this paper is just about the simulation. And for bouncing, we use virtual model control, and for leg swinging, we use velocity-based leg adjustment. For balancing, we just use the physical constraint, and we are working on that in future. And about the virtual model control, we consider a kind of virtual spring between foot and hip, and we change the stiffness and rest length of the foot, and with this we can inject energy to the system, and like delta T that you can see here, and or absorb the energy. And for leg adjustment, we use VBLA, velocity-based leg adjustment, in which we use velocity vector and gravity vector, the weighted average of these two to find the leg direction. And we compare the results of hopping of the robot, the simulation, and a human, and we found some similarities. And you can see here we just with just adjusting two parameters, we can switch from hopping in place to forward hopping, and again from forward hopping to hopping in place. With just adjustment of two parameters and with a very simple controller. These are the results showed for hopping height and the horizontal velocity. And these are results of simulation model and the real robot. And you can see the physical constraints that we have for balancing, and for some reasons we cannot implement the controller for the balancing in future. We want to do that. With these three layers of control, we can simply control the robot, and we can mimic some parts of the human gait. And in future, we are trying to implement the virtual pendulum postural control for balancing. Thank you for your attention, and see you in interactive session.
Good afternoon, everyone. I'm Zhen Yugan. I come from University of Michigan. Today, I'm going to talk about a passive simplex model of quadrupeds. When looking at nature, we can see that quadrupeds move in a large variety of different gaits depending on speed, terrain, or simply due to the preferences as a result of their morphology. These gaits are typically classified according to their footfall patterns and vertical ground reference forces. The footfall patterns show when left hand, left front, right hand legs are in stance in one stride cycle, whereas the vertical ground reference forces demonstrate the magnitude and shapes of the vertical forces when they are in stance. Different gaits normally have different footfall patterns and vertical ground reference forces. For example, walking, trotting, and galloping. In our work, we were asking ourselves, where do all these quadrupedal gaits come from, and what exactly are they? More precisely, we were trying to generate the most simple model that can explain all the quadrupedal gaits at the same time. Just like the slim model, our model consists of one rigid body as torso and four massless legs. Apart from having four legs, the only difference is that the main body has an extended mass and thus rotational inertia. Similar to the slim model, this is a passive model. There's no energy losses at collisions, and the system is energetically conservative. The main difficulty in finding a gate is to coordinate all four legs at the same time and find out proper initial guesses. So instead of using only two phases per leg, stance and flight, we add a third phase, and we call this the swing phase. It means that after liftoff, each leg had to wait for a certain amount of time before it can engage in ground contact again. This additional phase makes it possible to coordinate all sorts of footfall patterns in one single model. So far, we have identified 6 different gaits. Shown here are trotting and pacing. There are 2 B gaits because 2 legs are touching down almost at the same time. In addition to these 2 B gaits, we also found 4 B gaits. They are walking and trotting. The footfall pattern of these gaits are very similar, but each spring undergoes a double compression in walking and only a single compression in trotting. Here we compared the simulated vertical ground reference forces with experimental data of real horses. As you can see, they match very well. Besides the symmetrical gaits, we can also extend our search to asymmetrical gaits. For example, bounding and galloping. Here, the left and right side move independently. To summarize, using a very simple passive model, we were able to produce 6 kinds of different gaits. These gaits differ in their footfall pattern as well in the shape of the ground reference forces that they create. So in a way, we can think about gaits as different modes of nonlinear elastic oscillations, different modes that all propel the animals forward. Thanks.
I'm Jim Schmiedler from the University of Notre Dame. This is some work done largely by my now former PhD student, Dave Post, to enhance the robustness of planar bipeds that are controlled using the hybrid zero dynamics based control approach. So you may have heard yesterday Brian Buss from Michigan, where the HCD based control was originated in Jesse Grizzle's lab. He talked about this. We like the control strategy in my lab for controlling planar bipeds. It's hybrid in the sense that the stance dynamics are continuous, And then you have the discrete foot impacts, and that's important for our disturbance rejection strategies here. And then the zero dynamics, of course, are the unactuated dynamics when all the joint errors are driven to zero. So we apply virtual constraints that are shown here, where we slave the actuated degrees of freedom to the unactuated degree of freedom, which is shown as theta here. And so on our robot here, you can see it under the control of the virtual constraints. As the student moves the robot forward and backward, changing that unactuated coordinate, the actuated coordinates change accordingly. And so HZD was originally developed for point-foot bipeds, which this is the same robot with point feet in our lab. We've subsequently shown how you can rigorously prove the same strategy with curved feet bipeds, which is what we do now. And in this case, in this video, you'll see the robot runs into a barrier that slows its forward velocity. And note that it doesn't fall when it hits the barrier, it falls at the first step after the barrier, because essentially the forward velocity was not what the planned impact was. And so it falls backward and fails. And so that's the robustness we're trying to improve. Orbit stabilizing control is a strategy to overcome this, where you essentially measure the distance from the periodic orbit and add that as a factor in your control law. Gain scheduling is done here based on the unactuated coordinate and its velocity. That's a great idea. It's worked on a two-link biped. We have challenges implementing it on our robot for calculating it in real time. The gain scheduling is based on the simulation torques, and our experimental torques often don't match simulation quite so well because we don't have a detailed system ID. And then you also have to do a complicated measurement of the zero dynamics velocity, which tends to have noise problems due to the observer. And so what we do is we implement heuristics. We've got a linear factor that essentially leans in to accelerate. If you simulate the orbit stabilizing control, you can approximate it with these first order approximations on both the torso and the swing leg. So we're changing the virtual constraints in response to these. And so if you take a look here, this is the same deceleration on the left. And if you look carefully at the video on the right, we'll show it in slow motion here. They hit the barrier at basically at the exact same time. And it's a relatively subtle leaning forward of the torso that overcomes the obstacle. The same control law works very well for acceleration pushes. We can talk about that video subsequently. Thank you.
Hi everybody, my name is Arne Renau. I'm from FZI Karlsruhe, Germany, and I would like to talk about our reactive posture behaviors which we have developed for a six-legged walking robot which enables it to walk over steep inclines and large obstacles. So let me start with a short motivation. If you have a look at these application scenarios, you will see that they are very challenging, rough, and mainly hazardous. So I believe this is a perfect place to use robots instead of humans or dogs. So, and I then believe that legged robots are especially suited well to cope with these challenges. So let me give you a short introduction to the robot we have used as evaluation platform. This is Lauron 5, our six-legged walking robot, and it has 4 joints per leg. It has a Biro-inspired leg mounting, and due to this, it is actually able to manipulate with its both front legs. And although it's having cables attached in this video, it can actually operate up to 2 hours fully autonomously. It has an onboard PC, and it was mainly designed for rough terrain, climbing over large obstacles, and walking up steep inclines. So what do I present in this paper? We're using a behavior-based control approach in the ideas of Brooks and Albitz, and here we're implementing 3 independent posture behaviors which together create the stability and ensure the robot always coming over rough terrain. And a special focus in this paper is on the inclination behavior, which uses the ground inclination extracted from the leg points and an IMU, and then adapts the body inclination. And best I can show you in the video here, so we're lifting up Lauron. In this configuration, we're not using the delta joint adaptation, so you see Lauron sliding backwards on this plane. So if we turn that on in the next version of the experiment, you will see that the leg is rotating right close to the body, and this enables it to mainly keep its stable position there. And if we use this and combine all of these behaviors, Lauren is actually able to autonomously climb up inclines like this one with 15 degrees. So the robot has no knowledge at all of the environment. This is all reactive and behavior-based, and you can see it does that quite well. And if just in a few seconds, you will see it actually also can cope well with 25 degrees, which is already quite challenging. If you're interested in this, please come by, have a look at my work, and discuss with me in the interactive session.
Good afternoon. My name is Will Bosworth, and I want to share with you our work studying the effect of leg impedance on efficiency and stability in quadrupedal trotting. A bit over a year ago, the MIT Cheetah performed its first steady quadrupedal gait, a trot gait shown in this video. This controller relied on tuned limb impedance to propel and stabilize the body. This robot and previous locomotion studies have shown the importance of tuned joint impedance in locomotion, but we feel that further understanding the role of limb impedance is critical to developing high-performance locomotion machines. To explore this, we built a simplified model of the MIT Cheetah, which used tuned joint impedance to trot. With this model, we could measure the stability and efficiency of the gait as a function of limb impedance. Stability was measured by adding a ground height disturbance to the model as shown in the animation, and measuring the number of strides to return to a limit cycle. We studied 4 joint impedance values, stiffness and damping at both the knee and hip joint. In our gaits, each of the 4 legs used identical limb impedance values. A wide range of each of these values was tested using an exhaustive search of the state space. The study results show the performance of the model robot as a function of each of the 4 impedance values that were tested. The top figure shows the stability is more sensitive to knee impedance values, the 2 values with a distinct bell curve shape, than hip impedance. The bottom figure shows that energetic cost of transport did not vary significantly across the range of stable gaits. And in general, cost of transport did not correspond to stability. We compared the mechanical work performed by limbs in both the hardware and simulation. The shapes and magnitude of the mechanical work data showed strong similarity. In summary, we used a model study of a quadrupedal trotting gait to show that selecting knee impedance is more important to stability than hip impedance. This observation should be useful to anyone building or tuning a new locomotion robot. We also did not observe a strong relationship between stability and efficiency. This is important to explore further given the number of locomotion studies that focus entirely on energetic cost as their metric of success, since high-performance locomotion requires both stability and efficiency. Thank you.
Hello everyone, my name is Xu Cao. I'm from University of Delaware. Today I'm going to present my work on the energetics of quadrupedal bounding with and without torso compliance. The work is supported by NSF and ARL. As we know, conceptual models or templates have been very useful in the study of leg locomotion. For instance, the spring-loaded inverted pendulum has inspired the design of man-leg robots and the development of various intuitive control strategies. However, the slip is very useful in bipedal locomotion. When it comes to quadruped, it cannot capture some of the common gaits, such as bounding and galloping. The reason is that slip cannot capture the interactions between the torso and the legs. So in this study, we will propose a model to study quadrupedal bounding, which is a special case of galloping motion. And in particular, we are interested in the relationship between the torso compliance and the energetics. This is motivated by the biology research saying that animals like cheetah, they will use the elastic elements in their torso to recycle some of the energy used to swing the legs, thus reducing the cost of running. So to test this hypothesis, we consider both flexible and rigid torso configurations. In the flexible torso model, a torsional spring is inserted between the 2 segments of the torso to introduce compliance. And we consider non-trivial leg mass and inertia for both models. Based on that, we can measure the energy used to swing the legs. We also non-dimensionalize models so that their physical parameters can be captured by a small group of quantities. The bounding gate we studied consists of 2 flight phases and 2 stance phases. And to study this periodic motion, we used the point cloud map method. And our target is to find fixed points for this system that minimize the cost of transport, which is the consumed energy per travel distance and body weight. We analyzed the effects of the physical parameters on the COT, and there are some interesting findings. For example, when the torso is relatively short, then the flexible torso model is always more efficient than the rigid one. But when the torso becomes longer, then there exists a threshold value for the forward speed. Above that, the flexible torso model is more efficient, and below that, the rigid one is more efficient. And it's very interesting that this threshold value actually corresponds to the transition speed from trotting gait to galloping gait in animals running. So I would like to provide more details in the interactive session. Thank you.
Hello, my name is Jun An. I guess you're already familiar with this video of the MIT cheetah, which runs up to 6 meters per second or 22 kilometers per hour. Here I will present how we analyze the performance of the controller by the mathematical model and the simulation. This video shows that the trail running at 2 to 5 meters per second all converge to the closed trajectories. And we verified the local stability of those limit cycles using Poincare map analysis. As shown in the bottom, the flocking multipliers of each limit cycle all stay inside the unit circle, which guarantees asymptotic stability. However, flocking multiplier only concludes local stability under the small enough perturbation. Therefore, to investigate the performance of the system more practically, we simulated the system response under large perturbations. And as shown in these 3 plots, the model converges to its original limit cycle under various large perturbations. And this implies that the controller can modulate the speed of the robot, which is now proven by the actual hardware of the MIT cheetah. In this video, the controller is accelerating the robot model from 1 to 6 meters per second gradually. And our analysis also suggests and predicts the upper limit of the stable running speed. As shown in these figures, the Poincare map has one fixed point, which illustrates the stable period 1 gait at low speed. On the other hand, at a speed around 5.6 meters per second, we observed a clear period doubling bifurcation. And the model shows much richer dynamics as the speed increases. Period 4 gates and the successive additional, the cascade of period doubling bifurcation were observed, which may lead to chaotic dynamics at high speed. So it may suggest the upper limit of the stable running speed. Thank you very much for your attention, and I will discuss further in the upcoming interactive session.